topic of coronal activity in the Sun and other stars. After her graduate studies, she held a postdoctoral appointment at the Kavli Institute for Astrophysics and MIT in the Chandra HETG group. Her research focuses on understanding the heating mechanisms and X-ray emission processes in the hot outer layer of the atmosphere of the Sun and other stars by combining observations with advanced numerical modeling. Her interests encompass a wide range of astrophysical sources, including the Sun, late-type pre-main sequence, and early-type stars. Paula is also involved in development and operations of space instrumentation as a QI or instrument team member of several missions and of rocket experiments, including the Interface Region Imaging Spectrograph IRIS, the Hinode X-ray Telescope XRT, the SDO Atmospheric Imaging Assembly AIA, the Marshall Grazing Incidence X-ray Spectrometer, MAGIX, the High Resolution Coronal Imager HIC, and the upcoming multi-slit Solar Explorer MUSE, NASA MIDEX mission, and EUV High Throughput Spectroscopic Telescope EUVST mission. She will be speaking on observations signatures of coronal heating mechanisms in active region course.
Sorry, do we know how to do the slide and take up the whole screen? What they changed the new, but it's the same.
I don't know what
It is. I'm sorry to but this one is easier.
Yes.
Yeah. Okay.
All right. Well, first I would like to thank all of you for having me. It's such a pleasure to be here. It's been I was trying to remember, but I think it's been close to 10 years since I've been at HAO. It's a pleasure to see some familiar faces, some that I haven't seen since pre-pandemic, and some that are new faces for me. So thank you again. So I'm gonna talk a little bit about some work that I've done in the course of the past about 10 years with different instruments to try to understand a little bit the details of the coronal heating mechanism, specifically in the core of solar active regions. I'm going to give a brief introduction. I don't know how many of you are familiar, general solar physics with the corona. I'm assuming most of you, but just briefly, the coronal heating problem on the Sun, it's a very long-standing problem, and of course we know a lot about it, and we figure out lots of the basics, and there are some of the details that we're still trying to figure out. So there are lots of mechanisms that can be associated with coronal heating, including alpha waves, magnetic reconnection, flux emergence. There is possibly related to a mechanism that creates the chromospheric speakles. And we know that all of these processes are happening, but the importance of the different processes, different regions of the Sun can be quite different. So in the course of this talk, I'm mostly going to focus on the active region course, and I'm mostly talking about sort of quiescent emission, where quiescent for me means outside large flares. Because when we look at the hot emission of the Sun, the cores of the active regions is where we have most of the plasma, and where hot, above 3 million degrees or so. And when we look at this hot plasma, we can see that even outside large flares, it's always quite variable. Now we have, for instance, the last 10 plus year AIA that provides us with continuous high cadence observations at different temperatures, and we can see that in the channels they're most sensitive to the hot emission, like for instance the 94 angstrom, which is sensitive to emission from iron 18, so mostly above 5 million degrees. And the 131, which is sensitive to even hotter emission, but up to about 10 million degrees. We can see that the core of the active region, the emission is always kind of flickering and continuously going on and off. So there are several evidences that make us think that most of the heating in the core of the active region, this hot plasma, is due to magnetic reconnection. And I'm going to talk about some of this evidence. And as I was saying in my bio, I've always been interested. I'm mostly an observer, mostly using observations, but I'm always interested in combining the observations with predictions from state-of-the-art models. Because I think that it's really quite crucial to use the models in order to interpret our observations. And it's kind of a nice synergy, because when we compare observations and models, we can really improve the models as well, because we can see where they fail and what we need to improve. And at the same time, they're very necessary tool for the interpretation. And the other thing that I'm going to stress is also the use of observations that are looking at different atmospheric layers. So as I was saying, the topic of this talk is mostly coronal heating, but you will see that I'm going to use a lot of transition region and chromospheric emissions to figure out the coronal heating. So the connection between the different layers is fundamental, and when we can observe all these different layers at the same time, we can learn a lot more about the coronal. So here is just some examples of the type of I don't know why the movie in the background doesn't work.
It was going on the screen.
Oh, there you go. Okay. So we, as I was saying before, we do know that most of the heating is related to the magnetic field, and the magnetic field can create different types of processes. And in time, we've been developing detailed models for that. And some of the main candidates for the heating are alpha waves, so the magnetic wave heating, and here's just an example from some recent model from Van Ballehoen. And from magnetic reconnection, so for instance, braiding, and here's an example from 3D MHD models from Bifrost from the also group. So now we have, and of course, you know, here you have Matthias that works on NURM, and also the people that have developed the more and more complex models, which are very interesting, but they need to continuously be checked against observations to try to understand how we improve them. Okay, so as I was saying before, even if I'm going to talk about coronal heating, I'm not always just going to look at coronal emission. And here I'm explaining a little bit why. So by looking at the foot points of the hot loops, we can learn a lot. And the reason is that when we try to diagnose coronal heating by just looking at the coronal emission, you know, our progress is hampered by the fact that we have lots of effects that make it quite difficult to actually tie what we see coronal emission to the actual heating processes. In the corona, we have very efficient conduction. We have a very low initial emission measure at high temperatures. Some of the initial heating cannot really be observed because we don't have enough emission measure. We have non-equilibrium effects. So we have lots of non-local processes and the processes that make it quite hard to actually pin down the coronal heating by just looking at the coronal emission. However, we do know that likely this happens on very small spatial and temporal scales. So when we look at the foot points, and here I have an example. So here you can see in the AAA 94 emission, this is mostly emission above 5 million degrees. You see lots of variability. As I was saying before, we see lots of these hot loops. They're varying all the time. And on the right, instead, there is emission in mostly iron 12, so this is the AA 193 angstrom emission. And you can see that when we have these hot loops like here left, at the foot points here, you can see that there is a patch of moss, which is the foot points of these very hot loops, which is very continuously varying. So the transition region is very sensitive to the heating because essentially we have very large gradients in a very small region. And so when we have changes in the heating, we can see much more clearly changes in the emission in the transition region. When about 10 years ago, the IC rocket was launched, the first IC, we looked at that. So the patch of moss that I was pointing out before is observed here for about 5 minutes in IC. This is the IC moving top, and you can compare also the spatial properties with the corresponding AIA. This is just one of the still images of AIA. So the fact that we have much higher spatial and temporal resolution meant that we could actually see a lot of variability that was hidden in the AIA movies. We studied that and we tried to infer some properties of the coronal heating from there. And I think that there are some interesting results. But the problem is that we're also just looking at imaging observations, and so we have limited information. In principle, when we can look at the spectra, we can also have lots more information because we have much more constraints in terms of velocities and lots of other things. So when a year later, we started looking at IRIS observations. So IRIS is an instrument that mostly looks at the transition region and chromospheric emission. We tried to look for some similar type of event where we had also spectral information. So here you can see kind of a similar type of heating where we have the hot plasma that you can see in the bottom in the AA84 emission. And you can see how variable and bright the transition region emission is. In the top, there is the IRIS 1400 where we have mostly silicon-4 emission. And so we could study there that and for several of these points. So this looks a little bit like a mini flare. It's like a mini ribbon. And where we have these slits, which you can see maybe as the dark vertical line here, we had, for a few of these points, we had spectral information from IRIS. And it turned out that this was it was providing very advanced diagnostics for the coronal heating. So we could see that the brightness are short-lived. And when we looked at the silicon-4 emission, here you can see one of the examples in the bottom left. So here there are line curves in the several AAA and IRIS plasmas and lines. And here you can see an example of the silicon-4 spectrum as a function of time. So you can see that it's the brightening is very short-lived. You can see here it's of the order of like 20 seconds or so. And one thing that we noticed is that a few of these events showed blue shifts and a few showed red shifts. And so in order to interpret that, we needed to use some models to try to figure out what this Doppler shift could tell us. We used the Radin loop model. So this is a 1D model. So of course, it's limited in many ways, but the reason we use that is that it has a couple of very nice properties. One is that it includes non-local thermodynamic equilibrium, radiative transfer, and so we could also model the chromospheric emission that's observed by IRIS. And the other is that there is a module that allows us to model not only heating by conduction, essentially local heating by conduction, but also heating by nocturnal electrons. And the scenario, as I was saying before, it's a little bit like a mini flare. So we assume that there is a magnetic reconnection happening somewhere in the corona. There is acceleration of particles. The particles are streaming down, following the magnetic field lines, and they interact with the dense chromosphere. So when we did that, one advantage of using also the 1D model is that we can change the parameters and we can see how sensitive the observables are to the different parameters. And by doing that, we figured out that at least for this type of models, the only way to get a blue shift in the silicon-4 was to have non-thermal particles. And the reason for that is that essentially you need to have heating deposited lower down in the atmosphere so that you have a blue shift that is associated with the heating, at least at the beginning. And here you see one of our models. So this is the case where we have a total energy of 6 × 10⁻²⁴ Hertz, which is something of the order of a nanoflare. We have a non-thermal electron distribution with a cutoff energy of 10 keV. And here the models light curves and spectra, and we have some information of where the heating happens and where the emission measure changes. So here, essentially, we had a way to interpret our observations. And so we said, well, that's a very interesting diagnostic because, of course, the main way to study non-thermal particles is to use the direct emission from hard X-rays. But the RDX rays have limitations when you're looking at these very, very small events. They just don't have the sensitivity, they don't have the spatial and temporal resolution. So if we have an indirect new way to determine the properties of non-thermal particles, we can learn a lot. And for instance, one of the big questions is, whether there are these non-thermal particles in outside flares and these very small eating events, and whether they're important in terms of the energetics of the coronal. So as a follow-up work, we try to get some statistics. So first, this is a work that we published a few years ago, where we tried manually to gather a few of these events, and we found about 10 of these events. And we have about 30 or so foot points where we have this spectral information. And you can see here, they're just stills, and they show the iris emission on the left and the AAA hot emission on the right. And there is a big variety. We have kind of a bit larger events with very, very small events, and they all are similar in the sense they have brightening durations. They're under about a minute. But there is a very large range of properties. Even in a single one of these events, and I'll show some examples, when we look at the spectra, we have lots of different types of properties. And one thing that we also did going beyond the initial work is that in this case, we not only looked at the silicon-4, but we also looked at the atmospheric emission from carbon-2 and magnesium-2. So this is just one of the examples. So here you can see the iris emission, and you're going to see kind of the foot points of these three small loops on both sides. So this is one set of foot points, and this is another set of foot points that it's beneath the slit. So these are, for instance, some 3 pixels from this event. And these are, so each color here in the bottom corresponds to a different time. And here we're just covering about minutes, as you can see. And they're for different points, and we can see that there are quite different properties in terms of the spectral properties. And the top part is the light curves, and some properties for the silicon-4, so the Doppler shift, the thermal broadening for the silicon-4, and the magnesium-2 properties. So it's interesting because it means that most likely, even in these very small events, in different field lines, we can have quite different properties, which is, not new, but, when we look at the RDX ray observations, we kind of tend to think a little bit of a sort of monolithic behavior where we have certain properties for the non-thermal particles. They're kind of all the same. So this one can show you the hot emission. It's a very small event. It's a really tiny event. So it's a very small set of hot loops that we can see here. They're kind of appearing. We found some kind of common properties for this type of events for these hot loops. One thing is that even in the smallest events, we always find that the observations point to hot emission. And here there is, for instance, the example of the emission measure distribution as a function of time for this very tiny event. So even in these very small events, we find high temperatures. And this is another case of a paper we published a few years ago, where we also were lucky that we found the ice observation at the same time. And for this case, we also could see iron-23 emission, which is very short-lived, but it's there. So hot emission, even in the smallest event. And then the other thing is that it's quite interesting that intrigued us was the apparent morphology in the corona or for this type of events. So this is just a little bit of hand wavy, I have to say, but when we look at the coronal morphology, it's very suggestive of having something more like a large angle reconnection compared to the braiding, where you were thinking that essentially you have very small angle reconnection, that it's due to the shuffling of the points. So our current hypothesis is that maybe these hotter loops that we see in the cores of the active region might be more linked to flux emergence, where you might have flux emerging and interacting with pre-existing flux, and you might have more larger angle reconnection that leads to hotter temperatures. And we're trying to address this by looking at some recent Bifrost models of Viggo Arnstein that is looking at flux emergence, and it's looking more at the hot emission. there. Another thing that we did to expand the initial work was to expand the grid of heating models from the radiant simulations. And so here, we don't need to go into details, but we have a wide range of parameters in terms of the total energy, parameters of the electron beam, duration of the heating, and also we tried also to use the simulations to explore situations where we have a mix of the local heating and non-thermal electrons, which to me seems like the most natural case where you don't have everything either in the conduction or the non-thermal electrons, but you might have to mix those. And one important thing which I haven't touched too much upon before is the fact that in the models we realized that the observational response to the heating is crucially dependent on the initial conditions of the loop. So if you have initially a loop that is quite empty, it's mostly density, but if it's quite empty, you can have quite strong response, of course, to small events. If you have a very dense loop, you might need much larger energies, and the response is changing quite a bit. So from this first kind of expanded sample of events, of similar events of these hot loops with brightenings of the food points, we used the comparison between the observations and the models to kind of try to tell us whether we're going in the right direction. And here you see, for instance, on the right, some of the histograms that we got from the observations. So this, the black curves are the histograms, for instance, in the top for the Doppler velocities in the silicon-4, and the bottom ones are the intensity ratios between the chronospheric and the transition region emission. And here we didn't do a one-to-one modeling of each event, but we just wanted to see whether if we compare them with our grid of models, whether we are in the right bulk. So for the velocities, we can clearly see that we are. You might notice that the case for pure conduction, which is the red one here, is kind of a little bit at the extreme of the redshift there observed. And, that might point either to the fact that we are using two empty loops. So if we have a much denser loop, you can have smaller velocities, but also probably to the fact that we might have again a mix between the thermal conduction and the non-thermal particles. One new diagnostic that we found out was also that the magnesium-2 triplet emission, which is observed in the iris passband, is a powerful diagnostic of the non-thermal electrons, because essentially you're looking at heating lower down in the chromosphere. And we found that there is evidence of this non-thermal emission in about 4 of 10 of these events. And most important, we quickly realized that, when we are going to try to do the model for each of these events, when we have all of this information from different layers from the chromosphere and transition region, they really constrain quite well the heating properties. So to go beyond that and try to get a little bit more statistics, we decided that clearly selecting events by hand wasn't the way to go. So we used an automated algorithm for the mass variability detection. And this is work that Debbie Graham done a few years ago. So here you see an example for, again, the IC data set that I was showing before. So this is great, but we only have 3.5 minutes. So we have years and years on AA. And of course, with AA, we're not going to see all of them, but we can at least see a good part of them. So he developed this automated algorithm with certain criteria. I'm not going to go into the details of that, but this has allowed us really to dramatically expand the statistics of this type of events. So here, just to give an example, this was the algorithm applied to the same active region that I see observed. And you can see the red parts are where it detects these events, and you can see the mostly clustering at the foot points of these hot loops. So by using this algorithm, postdoc Lockheed has applied this algorithm to a large set of iris observations. So Kyun Cho has applied this algorithm to 4 different active regions that we observed for several days with iris. And for iris, I don't know if you're familiar with it, but it's nice in the pages in the database. You find the AIA data cubes. They're already aligned with iris, so that's very nice. We could directly use those and essentially apply the algorithm to the AIA data cubes. And then it was going to find where it finds this detection, whether we have the iris information. And so this way, he analyzed about 1,100 brightness. So now we're talking a little bit more about real statistics. And the 4 active regions also are quite different. There are some that are more quiet, some that are more active. So it could give us some more information about that. So these are the histograms. It's a little bit of a detailed paper, but it has a lot of interesting information. Here I'm mostly showing the histograms. So these are the histograms for instance, for the total intensity of the silicon-4, the non-thermal broadening of the silicon-4, the Doppler shifts of the silicon-4, and then some properties of the magnesium-2. And here, for instance, is the magnesium-2 triplet emission. The different colors are for the different active regions. And the symbols are again for our Radin model predictions. So we learned a lot from there. And interestingly, a lot of the results are quite similar to the much smaller sample that we analyzed before. So we see that there is evidence for non-thermal particles about a third of our observations, which is quite interesting. And I would like to also make the point that, here are the ones where we see the clear evidence of the non-thermal particles, but there are some models that include non-thermal particles, which, can be explained also by conduction. So it doesn't necessarily tell you that in the remaining 70%, there is no non-thermal particles. More active regions have more brightening. And one interesting thing is that, again, we're not doing a direct one-to-one modeling of each event, but we found out quite quickly that it is quite hard from a single model to fit every parameter that we observe for every event. So we need to expand our range of models, for instance, also in terms of our initial conditions. In the paper, I'm not gonna show it here, but he has an enormous table where essentially it looks at correlations between all the parameters, but it finds lots of quite interesting properties. Here I'm just showing just one of them. So here, for instance, it's looking at the non-thermal broadening of silicon-4 in these events as a function of the line of sight. So, we have for all these active regions, we have views for about 10 days or so. So we see essentially as the active region is shown a line of sight, whether we see a difference. And there is no clear correlation. And this is kind of putting probably some tight constraints, for instance, on alpha wave models, because for the alpha waves, you would expect lots of the non-thermal broadening to be due to the motions perpendicular to the magnetic field. And so you would expect some dependence on the line of sight if we assume, of course, that what we are seeing is that when we're looking at the chromospheric emission and transition region emission, that's perpendicular. The magnetic field is quite perpendicular to the surface. So we learned a lot of things. Of course, we haven't addressed all of the details of this. So, for instance, how energetically relevant these are, and so on. And we are expecting to make significant progress on this with new spectroscopic measurements that we're going to have, for instance, with MUSE. So MUSE is the multi-slit solar explorer. This has been selected as NASA MIDEX mission last year, and we're expecting a 2027 launch. It has 2 passbands for the context imager, which are shown here. One is 304 and one is 195. And this have a very high spatial resolution, very similar to the high C observations that I was showing before. And then we have 3 spectral bands, and we have 37 slits. So here there is the kind of a representation of the field of view of the spectra compared to the coronal imager. The spectral lines that we're focusing on are the 171, iron 9, the 284, iron 15, and then there is a 108 band that has both iron 19 and iron 21. So this is going to be quite revolutionary because, you know, having the spectral information in so many places at the same time, first, you're almost never going to miss an event again, because with the single slit, it's always hit or miss. And, you know, we're going to have very high, much higher spatial resolution and a very high cadence. So we're going to be able to cover, for instance, this field of view in 12 seconds at the same cadence as AIA, but having all the spectral information everywhere. Of course, it's, you know, it's not all great. There are complications because having the 37 slits means that we have also some mixing of the spatial and spectral dimension. So, you know, we've done lots of work on the disambiguation, and we've done lots of work in selecting only spectral lines where, you know, the line is very strong, there is not too much contamination from other lines and so on. But there is a lot of work that is going on in that direction. This is very quickly, Bart tomorrow is going to give a talk at NSO on Muse. So if you want to hear more, you're going to hear a lot more tomorrow about this. But this is just a very quick view of the science goals. So the you know, center is to try to, of course, address the physics of the solar corona and also the eruptions, condition of space weather. So here we see some examples of some of the science goals, like, you know, driving space weather models, the both reconnection and triggering flares, CMEs. And here you can see some of the topics that I was talking about. So what heats the solar corona, you know, to constrain the Austen wave from Spiegel's models, magnetic reconnection, and so on. And during the process of where the our proposal was under review, we did lots of work, and, you know, lots of you have participated into that, like Matthias has done lots of work for this, where we really use lots of models to make the point that ships can really constrain lots of these models, because the one of the problems is that now we have very sophisticated models, but the observations are often not good enough to constrain the models. So here I have just a couple of examples which are more relevant to the science that I was talking about. This is an example from Muran simulations from Sanja Danilovic, and here we're synthesizing the iron 19 emissions in the 108 panel. And, you know, here we're not only going to be able to have the information on the iron 19 emission everywhere along the loop, but we're going to have also the spectral information, which is very important to constrain the heating processes. And this is an example of the expectations for the Radin simulations that I talked about before in terms of the Muse observables. So in this case, we're going to add more information because essentially we're going to look higher up in the transition region. The examples that I was showing were mostly looking at the lower transition region and chromosphere. And if we have also information from the upper transition region, then we can constrain our models even better.
Can you see all of these all these wavelengths simultaneously?
Yeah. Yeah, we're going to observe all of the time in all of the spectral bands.
And are the iron 19 and 21, 104 both, 108 both of them?
Yeah. Yeah, they're there, but the 108 actually is our cleanest band. I think that it's going to be no issue really to look at those. The 284 is more complex because there's lots of lines and a broader band. But I think the 108 is going to be very nice to look at these small heating bands. And now I'm just going to, I have one last topic, which is kind of still in progress, but I was going to add some of these observations. So this is again a similar type of events as the ones that I showed before, but in this case, we have a simultaneous IRIS and SST observations. So the ground-based observations in this case were made with the new instrument Chromis there. So here we're looking at the movies in the calcium 2 K core, and you can see this sort of ribbon here. That is where we focus our attention. You can see the SST spatial resolution in this case is very high. It's about 100 kilometers. We have a little bit lower cadence. Instead, the IRIS has a very high temporal cadence, but a smaller spatial resolution. So this is the context from the upper transition region in the AA 171. You can see the Bragnings in there. You can see the hot loops in the AA 94. And let's see, we've done a different type of analysis exploiting the fact that we have the spectral information everywhere in the Chromis data. So here we have the calcium K spectra everywhere in the field of view. And what I did was to use K-mix clustering analysis to try to figure out whether there is a certain distribution of spectra which is more common in this ribbon compared to other places. And that turned out to be the case. And here I'm showing some examples. So let me show first. So these are, I used the 60 clusters, and the ones that I circled here and that they're showed, I'll show the other plot again, are the ones that are more commonly happening in the ribbon, and they're actually not happening anywhere else. And I'm showing here the spatial distribution for each time step. I'm showing with a different color the spatial distribution of that cluster. And here in the right is the representative spectral profile for that cluster. So this way, if we step through the time from the beginning of the event and we go on, we can see that there is very interesting coherence to the spectral properties. So you're going to see essentially that some places they start with the blue and then develop for the red. Like here, for instance, if you focus kind of on this bump, you're going to see the blue shift at the kind of purple profile first, and then it's replaced by the red profile. And so we have a couple of interesting things. So we see that there is a spatial and temporal coherence of these spectral properties in this ribbon. And now this part of the work that a PhD student in Oslo is doing also. Helle Bakke is working with Luke Rupen on the board, me, on trying to match these spectral profiles to our Radix simulations to do the interpretation. So, okay, so I would like to conclude then. I kind of took you on this kind of journey that we did in the last 10 years, where we looked at this type of events with lots of different instruments. I think we learned quite a few new things about the small heating events in the cores of the active regions. We found new diagnostic, even if they're indirect diagnostics of non-thermal particles that can tell us that these non-thermal particles can be produced even in the smallest events. And I think I stressed how important the cooperation, observations, and modeling is to try to understand these observations. These new diagnostics also suggest that these very small events are quite like scaled down versions of the larger flares in many aspects. I mean, of course, lots of the properties are different. Like, for instance, when we look at the non-thermal electron distributions, they tend to be a lot softer. They tend to be with different slopes and different low energy cutoff. But it's interesting that we do see the hot emission and the non-thermal particles in lots of these very small events. And also the fact that, again, when we observe an event with different types of observations that look at the different layers of the atmosphere, we can actually constrain coronal heating a lot better than if we just look at the corona. Thank you very much.
It's open for questions.
Thank you, Tom. Maybe we don't hear you. I don't know, do we?
Samaya,
Hey, Samaya.
Hey, Paula, nice to see you.
Yeah, nice to hear you.
How long are you here in town for?
We're in town for a few days, but tomorrow will be at NSO, but then we're gonna be on vacation.
Okay, all right, great. I just wondering because, you know, I just want to say hi. I did have a question about the real question about the radon model. So it was really, it's really interesting how you can derive some or constrain some component of the non-thermal electrons from just the magnesium 2 triplet emission. So is that model, I know you showed a couple different variations of the model. You kind of played around with different parameters.
Yeah.
What about height of the reconnection, where the reconnection is taking place? Because I would imagine that beaming that's happening that gives you the estimate would be different for different heights in the corona where reconnection is taking place. For instance, if it's really low down, how does that change the estimate of magnesium 2?
Yeah, it turns out as long as you're hitting mostly in the corona, it doesn't really make a difference. You know, if you're locally accelerating the particles, putting them already very low down, yeah, and then it's gonna matter. But if you just put them in the corona, it doesn't. I mean, we tried with a couple of cases and didn't make any difference. So we didn't explore, you know, much more than that. Although it will make a little bit of a difference if you have a very dense initial corona, then when you put the non-thermal particles, if they are fairly soft, they can interact with the material in the corona and they can lose more energy in the corona. So in that case, if you have a very dense initial atmosphere and you have a very asymmetric distribution in the loop, you might have a very different effect at the 2 points. So that can happen. We haven't explored too much about that because essentially if we have an initial very dense atmosphere, then you start needing energies which are much larger than the nanoflare energies that we were interested in.
Okay. Okay. And so the magnesium, so what exactly does that emission give you? I saw, yes, actually, can you show this plot? Which of those plots, can you go back to the CHO plot?
Yes.
Of the different observations that he had. Yeah, so which of those, so in the lower left panel is the one you're showing that has evidence of, so what components are you getting from the magnesium 2? What parameters are you actually?
So in this interpretation, essentially, the positive values are where you have the magnesium 2 triplet in emission. And so you can see essentially that models that have significant non-thermal particles are predicting a positive value, so magnesium triplet emission. The negative ones are the cases, for instance, here the conduction case. C1 is the purely conduction case, where essentially you have the absorption case. So all of these models, since we were interested in the thermal particles with different parameters, they are pretty much all of them predicting positive case. And you can see that here you have a asymmetric distribution. You have lots of those cases which are with negative emission. And again, here there might be some subtleties also because we used the equivalent width, and it might not be necessarily a perfect measure, but we were trying to do some automatic analysis of the spectra.
Okay, it's interesting. It's really cool technique. Thanks.
Thank you, Samaya.
Travis and then Matthias.
So from what I understand, both Parker and the Solar Orbiter have seen evidence that these nanoflare events kind of cluster around supergranular boundaries. Do you see any evidence of that in the observations that you've looked at? And can you give me a sense of what fraction of the coronal heating problem could nanoflares potentially solve? Is it all of it, or is it a partial solution?
See, I think that the answer depends a little bit on your definition of nanoflares. I mean, if you ask Jim Klimchak, he will tell you, well, it's everything nanoflares. You know, if you have alpha waves, but you have just like bursty kind of events, they're also nanoflares. So as I say, my feeling is that the fact that you have this very small events and small temporal and spatial scales, a lot of the quiescent corona is going to be dominated by this. But again, some of it might be more related to magnetic reconnection and some more to alpha waves. The alpha wave models, they're still a little behind, I think, the more braiding-based models. So far they seem to indicate that it's very hard with the alpha waves to produce hot plasma, and that's another thing that makes me think that when you're looking at the active region cores, most likely we're looking at the magnetic reconnection. And we think that maybe when you're looking at the hottest loops, as I was saying before, it's not just a pure shuffling of the foot points, but maybe something more related to larger events like flux emergence and interactions with the existing field. So I think that I don't know. I don't really have a very good quantitative answer, but my feeling is that nanoflares, depending on how you define it, can explain quite a lot of the coronal heating. But then the devil is in the details.
Yeah. And the association with supergranular boundaries, is that robust? Or?
I don't know too much about that, but I think that that's mostly in more quiet sun where you have, these kind of things. There in active regions, you have different type of configurations. Yes.
Yeah, which fraction of the nanoflare energy goes into the non-thermal particles versus the thermal plasma?
Yeah, so this is one place where we need to expand our grid of models. So far, for instance, when we use the hybrid models, I think we mostly put half in the non-thermal particles and half in the direct heating and conduction. So it's probably a wide range, and we need to find an efficient way to do modeling that it's much more constrained by a specific observations. It's a little bit, it takes a little bit of time because with Radin, for some reason, it's a little bit cumbersome to come up with different initial conditions. Once you have the initial conditions, then it's easy to change the other parameters. But to come up with a model that's stable and kind of reflects the initial condition of each of those events, it's a little bit cumbersome. So we're not quite there yet. But, so far, I think we explored mostly kind of half and half. But it's not really guided by anything in particular. It's a very ad hoc assumption.
Question.
Yeah, hi, Paula. Yeah, really nice talk. I'm in Florida at the moment, so that's why I'm not there in person. We're from
Enjoy.
tomorrow. Florida?
Yeah.
Yeah, where woke goes to die. But the internet's terrible here. So if I fade out, it's because my I actually had an instrumental question, and that is that all the new missions that you were talking about are basically looking at extreme ultraviolet or ultra soft X-ray lines down around 100 angstroms or so. And how much of an issue is it that the chromosphere is has a lot of neutral hydrogen in it, and the opacity in the Lyman continuum is going to be pretty high, maybe even down at 100 angstroms. And so are you really going to be able to see down to the to the lowest levels of the foot points at the base of the chromosphere? Or will there be sort of a horizon beyond which we won't be able to see because of the neutral hydrogen opacity?
I mean, the pass bands that we're looking at with Muse, for instance, they're like pass bands that we observe with SDO. So we're looking like at the upper transition region emission in the 171. I expect that we're going to see the same events that we would see with SDO, just a with better spatial and temporal resolution and the spectral information.
Yes, I agree. I'm just wondering if there are hidden events that you can't see because they're absorbed by the neutral hydrogen. And maybe I should have expressed it this way. If you took a simultaneous observation with IRIS looking at iron 21, making long exposures so that you could pick up the coronal forbidden line, and then you looked in the EUV or the ultrasoft X-rays at one of the iron 21 lines there, would you see the same thing? Or might there be events at the base of the chromosphere, very deep down, energetic events whose radiation would not be able to pass through the chromosphere at the shorter wavelengths?
I would think that, if there are such events, they're probably a very small minority. And if they're so buried in the atmosphere, they probably don't matter very much for the larger corona. So you might have, some special events, like whatever, like bombs and so on, where you have very large energy release. It's very low down, but they're probably not very relevant for the coronal energetics because, you're just releasing lots of the energy directly in the lower atmosphere. Not sure I'm answering your question, Tom. But
Maybe it just needs really a calculation, and you're probably right that the lower atmosphere.
I think Bart wants to chime in.
Hey, Tom. So I think we tried to look for those kinds of events when the forbidden lines that IRIS sees.
Okay.
We've never found any evidence for them that we could believe. Even in these UV bursts that are pretty violent events, there's very little evidence for emission from the 1349 and the iron 21 is such a faint line.
Yes.
How you've actually looked at that? We haven't found anything.
Yeah, we looked at the iron 12 and we just couldn't find anything. We looked at lots of those and it just doesn't seem to produce those high temperatures.
Yeah, we had Leisha look at iron 21.
Yes,
Yeah, I think you guys are right. The iron 12 would actually be a better place to look. But if you're not seeing anything, then I withdraw my comment.
Yeah.
Yes, Radin has been used a lot of times for big flares, right? And one of the things that it could never have produced, or the observation model, was the speed and the evolutionary time of how the spectral lines would respond. Particularly, the model was much faster than what you could observe. Is this true also for these models?
So in terms of the time scales, we're looking at very short time scales in our case. I think that most of our models have 10-second heating, and the time scales are very, very similar. The line shape of the magnesium 2 and the carbon 2 is not, is certainly missing something in the model. So, but in terms of time scales, I think they're quite similar. If you look at the light curves, in our papers, we show some of the light curves and compare them with the observations, and they're quite similar. Line shape, we're not quite there yet. But,
Is be an indication that even in that difference, you might have, collection of smaller things?
yeah, most likely. But it's a little complicated to think how to explore the parameter space when you start, because as soon as you start adding free parameters, you can probably go crazy with it.
Hi. Does the existence of the accelerated electrons allow you to put constraints on the geometry of the reconnection sites? For example, do we expect a higher frequency of non-thermal particles if the crossing angle is large compared to nearly parallel reconnection? Maybe that's a question for the other MHD people in the room, but I was just wondering if...
It's an interesting question, but yeah, I don't know the answer to that. I'm hoping that, this type of work can provide constraints to the people that are actually doing the modeling for this type of particle acceleration and so on, but I don't know the answer to that.
Any other questions from the room or from online? Okay. Let's thank our speaker again for